third day of the conference. It's been a blast so far, and we have sessions this morning focusing on measurement and quantum field theory. And so, and then we'll have 2 talks and a panel discussion. And then for those of you sticking around, we then shift to the graduate LMP conference after lunch. So we'll have lunch upstairs as usual on the 4th floor. But then after lunch, we'll be moving over to the philosophy department, which is a short walk. It's over at Stevenson Hall. And then we'll switch to the graduate conference program. So I hope some of you will be sticking with us for that. It looks like a great lineup as well. It's a real pleasure to start off this morning by introducing my colleague from nearby, Doreen Fraser, who's coming over from Waterloo, and her talk is on philosophical implications of measurement in QFT. And she's a co-organizer for the conference. So
and thank you to Chris for doing all the actual work. It's been a really, thank you to everyone who's presented already. It's been a really constructive, fruitful, productive couple of days for me anyway, of listening to the discussions between various people and some really, lots of things to think about from the talks as well. Okay, so what I'm going to talk about today is part of a very big project that I've been working on for the last several years now in collaboration with Maria Papiorgio, who is a PhD student who has 3 co-supervisors. So she's at the University of Waterloo, and Eduardo's one of her supervisors there, and QFT camp as well. And she's also supervised by Harris Anastopoulos at University of Hudson. So this has been a very deep collaboration between the 2 of us. So some of what I'm going to be talking about is stuff that Maria has been mostly working on. She didn't want her name on this paper because there's some philosophical stuff that she's deciding whether she agrees with this part or not. But so this is a big project that now there's this philosophy paper for philosophers that's going to be that's a manuscript will be ready soon. There is also a history paper which talks about the history of some of the developments I'm going to talk about today. And then the main paper is going to be a review paper which reviews some of this material. So I've been primarily collaborating with Maria on this particular research, but I've also really benefited from Eduardo's group. It has a big group working on RQI, relativistic quantum information, and so Eduardo and more of his students have really helped me to understand what's going on here. I think this is an area in which there's a lot of interesting philosophical issues that philosophers have been talking about for a while now with regards to quantum field theory. And now they're coming to the point where there's practical implications for different views that you take. And so this is an area in which I think it's going to be very fruitful for philosophers to think more about these issues. But it's also the kind of area where there's a lot you need to learn in order to get to a point where you can say something interesting. So I'm grateful to be part of this collaboration to be able to learn about this. Okay, so here is what my talk is going to be about. So there's quite a bit of setup here to explain to you what my talk is actually going to be about. So that's going to be the first part. What I'm going to do is I'm going to try to give you a quick survey of the landscape, but that is more than you can do in one talk. I'm going to then zero in on one particular proposal for a measurement theory for quantum field theory, local measurement theory for quantum field theory, which is the Fuster-Gark measurement framework for a QFT, which has been proposed in the last couple of years. And then I'm going to draw some of the immediate interpretive consequences and gesture at where there's a lot more work to be done. Okay, so, I should say, so QFT here. One thing the logical empiricists were right about is that there's a lot of ambiguity in the use of terminology in the sciences, and that leads to unproductive discussions a lot of the time. So I want to be clear that in this talk, what I mean is quantum field theory is quantum field theory combined with the special theory of relativity. And I see that, and we had quite a bit of discussion about this yesterday. I have a particular story about how that fits in with other, both classical and quantum theories, but I wanted to make it clear that this is what I'm talking about today. Okay, So I'm going to do the physics setup first, and then I'm going to talk about how this fits into the existing philosophy literature on questions about relativity and quantum theory and measurement. Okay, so here's the central question. So in non-relativistic quantum mechanics, which some people just describe as quantum theory, we have a well-established formalism for quantum theory, and we also have a well-worked-out quantum measurement theory to go with that physical quantum theory. So here, this started really with von Neumann, and then there's the Hooter's rule, and then there's a lot more recent work on this in by Bush and by collaborators. Okay, so here's the question. So you haven't missed anything yet. I'm just doing the setup. Okay. This is just the setup. Okay, so here's the question I'm asking here. Well, I'm not asking it. People who are thinking about measurements on local regions in quantum field theory are asking this question. Okay, so you have quantum theory plus quantum measurement theory. That's fairly well understood by now. How does that change when you go to relativistic quantum field theory? Well, we have quantum field theory, and then we have a question mark about how you represent local measurements. Okay, so what do I mean by that? Why does QFT need its own local theory? Why is there a question mark there? Well, I think it's useful to start by thinking about this historically. So Alex has a really great paper explaining the lead up to the formulation of QED, which has a great title that emphasizes that in non-relativistic quantum mechanics, you have an instantaneous state or stationary state, and that withers away in attempts to formulate relativistic quantum theory in various programs in the 1930s and 1940s. And it eventually results in the adoption of what we're all familiar with in QFT as the primary way of representing measurements, and that's the adoption of an asymptotic scattering theory for QED. So one answer to this question is you need to, now it's become important to think about whether we can undo that, right? Whether you can represent measurements in a way that's not asymptotic, where you're not taking the limits to infinite early and late times. Okay, so why is that important? There's also an important dialectical context here. You might say, okay, well, why can't I just take the very well worked out quantum measurement theory that we have, which has been used with non-relativistic quantum mechanics, but why can't I just apply that straightforwardly to relativistic quantum field theory? Well, there's a bunch to say about this, but one reason that's become prominent in this literature on measurement theory for quantum field theory is a paper by Raphael Sorkin, in 1993, where it talks about what he calls impossible measurement results. So the problem here is that if you take a very minimal framework for relativistic quantum theory, which includes microcausality, so you're including the assumption that O1 and O3 are space-like separated, so the operators you find out of the operators in these regions commute. But consider what happens if you take this intervening space-time region O2, and we're going to do an intervention. It's just what he calls a unitary kick, but it's just applying a unitary operator to this into the system in this region here. And then, so this is a field system that we're describing to use it as scalar field theory. Well, not full quantum field theory, but it's at least vacuum state field theory. And then you do a non-selective measurement on O2. Then it turns out that the expectation values for observables on this system in O3 are going to depend on on the parameter for the unitary operation here. Okay, so that means you have space-like dependence of the expectation values here on this, what you've done in the space-like region here. So that's superliminal signaling. So that's something we don't want in a measurement theory for relativistic quantum theory. Okay, so that's one motivation. There's lots actually more to say about that, but that's one motivation. Finally, this is very important, that there's a practical context here, of course, and this is, I think, particularly important to Eduardo. So why are we thinking about this now? We're thinking about this now because due to the rise of quantum information theory, which is very an important area in research in quantum theory as a whole, it's important to be able to think about relativistic processes in the context of quantum information theory, both on the theoretical side and then on the experimental side. So I think this is also important, that the kinds of experiments people are interested in, both modeling on the theoretical side and hopefully actually doing, are the types of experiments where now relativistic effects are going to be important. So this is why, if you're interested in relativistic effects, the fact that you do measurements locally is going to start mattering in a way in which, like scattering, asymptotic scattering theory, if you're actually trying to describe what happens at the LHC is okay. This is a context in which you're starting to care about what happens in local regions. Okay, so that's the physics setup. There's also philosophical context. Here I want to situate this appropriately in the existing philosophical literature. So some people, maybe even some people in this room, have engaged in philosophical debates about which formulation of quantum field theory is the best one to use as a starting point for philosophical analysis. So some people say you should think about algebraic QFT as a starting point. Other people say no, you should use mainstream QFT. So I think that while the details of that are going to come in at some level past what I'm going to talk about today, that's actually not the main issue I'm talking about here, right? So this lack of a local measurement theory is a gap in AQFT, and it's also a gap in mainstream approaches to quantum field theory, right? So, so that's actually not the main issue I'm talking about. There's of course been a lot of careful philosophical work on questions which have something to do with thinking about the peaceful coexistence between relativity theory and quantum theory. And so I think one general strategy for engaging in this kind of work that's been done for a long time is to interpret quantum theory, so the strategy for interpreting quantum theory and special relativity together is to start from non-relativistic quantum mechanics and its interpretations, and then to ask whether extensions to quantum field theory are possible. So Emily did a really nice job of this in her talk, surveying a bunch of ways in which people are doing this. I think attempted Bohmian QFT are also in this example, something in this tradition. So I wanted to draw a contrast between that work and this kind of different strategy that I'm going to be employing here, right? So the different strategy I'm going to be considering is, instead of starting with non-relativistic quantum mechanics, let's try to formulate a measurement theory for quantum field theory, and then from there, after you develop the appropriate relativistic formalism for representing measurement, then you interpret that. Okay, so so you might expect actually that these two lines of trying to answer basic interpretive questions about how relativity theory and quantum theory are going to converge at a certain point, but I wanted to point out this is quite a different style of argument than we've seen in most of the philosophical engagement to this point. I should say, actually, I just realized that I left out from my references at the end an important paper, that here is one paper which is a recent paper. It's called something like the pragmatic measurement problem in quantum field theory. So one paper which takes the second approach, but talks about measurement in quite it approaches interpretive issues in quite a different way than I do. Sorry, is this impossible to see?
Yeah.
Yeah.
Just read it.
So this is Grimmer. So Dan Grimmer, who was a student in Eduardo's group and is now doing a DPhil in philosophy at Oxford, has a draft paper about on the archive about which is called something like the pragmatic measurement problem in quantum field theory. So that's, I wanted to give you another example of something from the second spirit that's also very recent. Okay. Finally, of course, you can't talk about measurement without talking about the measurement problem. So I wanted to make it really clear that what I'm going to be talking about for the most part before I get to the interpretive piece of my talk is the question of how you develop a formalism for measurement theory in quantum field theory that has the nice relativistic appropriate properties that you want. So there's a bunch of different ways of going about doing this, but one thing that's clear in everybody's mind is that solving the measurement problem is not an immediate goal of formulating a measurement theory for QFT. So this is the cartoon way I think about it, and I'll come back to this at the end. But if you think about where one standard formulation of the measurement problem comes from in non-relativistic quantum mechanics, you take non-relativistic quantum mechanics, you take the quantum measurement theory for it, you can say like Luther's rule, something like that, and then you try to interpret it and you get the measurement problem with some other interpretive assumptions. Okay, so exactly the parallel thing you have in when you move over to quantum field theory, or I mean relativistic here to be clear. So in relativistic quantum, we have relativistic quantum field theory, different ways to formulate that. The question I'm going to mostly be talking about is this formal one, and what's the counterpart to this over here, the formalism. But then you would expect that you're going to get something over here. The point I'm going to make later on is these are question marks because you would naturally expect when you change the theory and you change the measurement theory that what form the measurement problem takes is going to be different in this kind of context, as we'll see it is. Okay, so I'm going to be focusing on an AQFT proposal for measurement theory, but I think it's also really important to just have a sense that this is one of a number of proposals, so I realize that I'm probably not going to have enough time to talk about this, but let me highlight one proposal, which is the second one. So the second one is detector-based measurement theory, which Eduardo has been instrumental in developing. So here's the strategy there. We use quantum field theory to model the system, and then we couple it to a detector, and we use non-relativistic quantum mechanics and the measurement theory, including projection postulate, to represent the outcomes of measurements on detectors, and then you can consider what is induced on the field when you represent measurements in this way. So of course, this involves coupling a non-relativistic system to a fully relativistic quantum field theory system. So it involves sort of judiciously choosing the coupling between the detector, which is non-relativistic, and the system. And the upshot of it is you then can do calculations and you can decide which regions are going to be the regions in which you trust this this representation of the way measurement is working, and there's going to be superluminal signaling from Sorkin type impossible measurement scenarios. It's not going to be ruled out in principle, but you can convince yourself it's like at some like higher order of perturbation theory, so it's negligible, right? So those are going to be the regimes in which you would trust this way of modeling measurement outcomes. I'll highlight number 3. In contrast, another way of going is to try to do everything in QFT. So model the system using QFT, and model the detector or the probe using QFT. And so this is the route that Fuster and Burke take, which is the FB framework. So here you can then, once you set things up properly, prove that there's no superluminal signaling in principle because everything's fully relativistic. The third one I really want to emphasize here is what I have as number 4. So another way of going is we have different ways of thinking about quantum theory operationally. So you can look at the abstract operational, you can look at the operational framework we developed for quantum theory. Think about how to make those more abstract. So think about probes and how they compose in an abstract way, and then develop concrete implementations of that abstract operational framework that are going to be appropriate for quantum field theory. So so this is something that an approach that Robert Opel has taken, and this is what Adam and Tia is going to be talking about in her talk next. Okay, there's other things happening here too. So, as a starting point for understanding what's happening in the algebraic approach to setting up a measurement theory for QFT, it's helpful to go back and think about what the original operational interpretation of AQFT involved. So at the end, I'm going to come back and contrast what you get out of the new measurement theory with the picture that you get traditionally when setting up AQFT. Okay, so this is a picture that goes back to, this is an interpretation that goes back to Hogg and Kassler, but I think it really persists throughout Hogg's work on AQFT. So the idea here is that you have algebras associated with local regions of space-time, and the algebra represents operations that can be performed in those local regions of space-time. So you can associate with this a Heisenberg picture representation in the sense that it's going to be when there's no interventions happening and you're just representing the internal dynamics of the system, that dynamics is going to be carried by the operators, and then the states are not time dependent. But then you can model in the same way we do in ordinary quantum mechanics, often external interventions on the system as a state update. So this actually all looks like local measurement theory, like maybe you might think like the kind of thing that I was looking for at the beginning when I had those question marks. It's not really, for several reasons, right? Well, one reason is this is all an abstract schema, right? If you say, okay, I'm going to do this measurement in my lab, what does that correspond to in my algebra? Or like, what equivalence class of things does that correspond to in terms of operations on my algebraic representation? There's not really an answer for that. And so then you might ask, okay, so how does this relate at all to empirical quantities? How does this relate to the things we predict? And the answer there is actually you go back to asymptotic scattering theory. And so one of the things Hogg did early on, partly thinking about Hogg's theorem, was developing Hogg-Ruel scattering theory. And so what you do is you relate the local observables to and this is a quote from that 1964 paper, quantities of direct physical interest such as particle masses and collision cross sections. So ultimately, the empirical content comes in through scattering in this approach as well. Okay. So as I just said, the FP measurement framework, as we see, is going to depart in significant respects from this traditional operational interpretation of AQFT. I have a big debt here to Laura's work on the operational interpretation of QFT you get here, because even before you get to thinking about measurements, there's lots of conceptual puzzles here, and this doesn't actually quite make sense. So I think that thinking through some of the things that Laura's thought about very carefully is a useful way to see how there's the seeds of breakdown here, but even before you get to thinking about adding a measurement theory to AQFT. Okay, so I'm going to proceed in steps here and try to give you a high-level overview of what the key moves are in much more detailed story that's lying in the background. Okay, so references here. There's a paper from 2020 by Stern and Berg called Quantum Fields and Local Measurements. There's a paper that came out like 2 weeks ago, which is an encyclopedia article for an encyclopedia that's coming out. That's where I would start. That one is actually a lot shorter, and it cleans up the presentation of some things from the initial paper. But those are the two main references that I'm working from here. Okay, so there's nothing on this slide that has anything to do with measurement yet. As I said, the main strategy here is going to be you have a system, you have a probe, you're going to couple them together, but you're going to describe both of them using AQFT. So first we have to say what it means to describe a system using AQFT, and this is an axiomatic approach. So you have this axiomatic, you posit a set of axioms, and this is how you're going to describe your systems. So for people who are familiar with traditional ways of representing a QFT, I wanted to flag a couple of differences here. This is some of the background here is Fuster in particular is thinking about locally covariant QFT. There's a more general version of what I'm doing here that involves actually collections of spacetimes rather than picking one spacetime. And so this is intended to be generalizable. But here's what I want to emphasize. So first of all, we're going to define global algebras associated with, in this case, a globally hyperbolic spacetime. So we're not just talking about Minkowski spacetime. We're also going to use star algebras rather than C-star algebras. So the reason for that is because the next step's going to be trying to figure out how to parallel the development of quantum measurement theory for algebraic quantum field theory. And so we want to have POVMs, right? So we're going to relax what algebras we want. The thing that's going to be really key for making everything work and come out to be nice and Lorentz covariance, but also to eliminate these signaling problems that come up in other approaches, is the time slice property. So this is a abstract way of positing in dynamics. So sometimes it's called the existence of the dynamics postulate by Fuster elsewhere. So the idea here is, so M is always going to be our big space time here, N is region within this bigger space time. So if our region N contains a Cauchy surface for M, then there's going to be an isomorphism, which locally embeds, and the algebra that we define over local region N to the whole space time M. I'll have a picture for that in a second. Okay, so here is the goal. So the goal is to represent the system, the probe, and the coupling between them using a QFT of this particular flavor that I just had up there. And we're going to, as a strategy for doing this, we're going to follow the same strategy as in quantum measurement theory. So actually what they do is they just take chapter 10 of Bush and collaborators' book on quantum measurement, and they go through all the steps, but and I'll have this in another slide, they make it appropriate for, the mathematical derivations appropriate for this particular context of QFT. And then we're going to derive a measurement theory for a QFT, including the state update rule, which is the part I'm going to focus on here. Okay, so in order to do this, we are going to do something very clever. And I think this is actually the key that makes the whole thing work so nicely. So I said that we don't want to have asymptotic scattering theory. But it would be nice to have a similar way of representing the dynamics. And so what they introduce is a sort of, it's more abstract, but it's an abstract version of scattering theory that's for bounded regions instead of being asymptotic. So here is how that works. So here is a picture of of our spacetime. And so Ks are always going to be the regions in which you have coupling between the system and probes. That's the region in which they're interacting. So they interact locally here in the causal path of K. They're not, you assume that your probe and your system are not interacting. Then you're going to have your probe and system go off after K, and they're not interacting anymore. Then you're going to measure your probe, and then you're going to be, you're going to have induced observables for your system that you're going to be inferring from measurements of your probe. Okay, so so anticipating the fact that we're going to be applying the time slice property. I have here an example of a Cauchy surface S, and the Cauchy surface is a Cauchy surface in region M plus. So the region M plus is the complement of the causal past of K. So it's everything. This gets too complicated because I shade everything, but so it's everything outside of the purple is the region M plus. And so that's an example of a Cauchy surface for M plus. And L is an example of a region in which we could be trying to make a measurement. And it's a region which is also in M plus. Okay, so here's where the scattering theory comes in. So we're going to introduce an algebra, several algebras, to represent our systems. We're going to introduce a sort of master algebra C, which is going to represent the coupled system and probe, so our two systems together. So there's another object we're going to be interested in because that's all I wrote down for that, right? And that's kind of going to, that's the whole problem here is that's not a really convenient thing to work with, and we can do better than that using the scattering theory. So also we're interested in the uncoupled algebra. So P here, so that's U, so P is the probe algebra, and S is the algebra just for the system. And so C, so our coupled system probe algebra is going to be is isomorphic to our uncoupled algebra in the region N minus, which is everything outside the causal future of our interaction region of the probe and system, of anything outside of the causal future of K. So for example, and M plus as well. So this is going to be key, right? So we have something so here's the intuition here. The intuition is there's something very complicated going on in K. To get a handle on what's going on, we're going to consider the simpler uncoupled algebra, which is going to give us a handle on what's going on in the causal past, at least, and N plus and N minus. And so this is going to allow us to establish isomorphisms, so you can show that these exist on a case-by-case basis. Yeah.
I think I just missed this, but what's M minus?
So M minus is, so M plus is everything outside the causal past, M minus is everything outside the causal future.
Ah.
Yeah. Okay. So, we now have two types of isomorphisms, which we can use to construct our scattering, it's actually an isomorphism, there's a morphism, scattering isomorphism. So essentially, what we're going to do is we're interested in observables in the M plus region, which is going to be the region in which we're going to be trying to extract information. We're going to measure our probe and we're going to extract information from it about our system. So essentially what we're going to be doing is we're going to be mapping observables from this uncoupled algebra in M plus to, and this is backwards to ordinary scattering theory in time direction, but it's fine. And we're going to map those to observables in the past in this uncoupled algebra. We need C, because that's the complicated thing that's happening in the interaction region. So that's where important physics is happening. So what we're going to be doing here is we're going to be using, we're going to be working C in the internal stages. So we have two types of isomorphisms that are going to be working here, right? One is the isomorphisms, which are the local embeddings from the time slice property, which are going to allow us either within U or within C to map to different space-time regions. And then the second set of isomorphisms is going to be outside of K, where we can map the uncoupled algebra to our coupled algebra. Okay. So at this point, I haven't said about anything other than algebras. The states are going to come next. Okay, so what we actually care about is the state update rules. So as I said, the strategy here is going to be to follow all the steps of quantum measurement theory to derive state update rules. So what do I mean by that? I mean, if you are working within quantum measurement theory, the first thing you do is you define a measurement scheme that specifies a correspondence between the probe observables, which are the things that you measure, so you do measurements on your probe, and the induced system observables. And then you define instruments which describe the system in light of these measurements that you do of the probe observables. And that's what you use to generate your state update rules. Okay, so here, you do the same thing for a QFT as I was saying. This is like, you do a similar kind of thing, and it's analogous, except we're going to use the scattering morphism because that's going to contain the dynamics, essentially, as well as the tracing out, as you can probably see from the algebraic presentation. We're also going to stick to abstract star algebras. We're not going to be constructing any Hilbert space representations, unlike what you would be doing with quantum measurement theory. And here's the key thing, right, is we've already made the space-time dependence of our algebras explicit. It's already part of our representation. So after you set up your state update rules and figure out how this all works, you can infer localization properties. Okay, so that's something you derive rather than something that's, and I'll show you an example of that later on. Okay, so this is the part where so then they do there's a bunch of details here that I'm gonna skip. So, as important background, I think it's important to keep in mind what we're actually doing here. This is going to factor into my interpretive moves later on, right? So, we're going to derive state update rules, which is going to be important for practical purposes, for convenience, as an exercise in bookkeeping, however you want to put it. But we actually already have everything, right? So, I just did the algebras. We have some state over our coupled algebra, and I didn't put the times in here for reasons I'll come obvious in a minute, but that's like a state. This is like our algebra for all of our space-time. We have this state for all of our space-time. So that's like everything, right? So that's all actual descriptions of what's going on in the world, but what we're gonna do is, that's not that useful for actually doing stuff with and figuring out what's going on. So what we're gonna do is we're going to derive state update rules to be able to figure out what's going on with the system, right? Because that's what we're doing here. We've set this whole thing up, we've coupled it to the probe, but at the end of the day, we really care about what's happening with our system, which is the target of the investigation. Okay, so following the usual strategy in quantum measurement theory, the thing that will be the updated state is going to be an updated algebraic state, omega primed, and that's the state over the system algebra that is going to assign the correct post-measurement conditional probabilities for our system. And the condition here is that they're conditional on observation of some probe effect in our probe algebra P. So this condition on what kind of state we want is exactly the same thing as you would find in ordinary quantum measurement theory. You want right conditional probabilities, and you're conditioning on the same kind of thing as you do in quantum measurement theory, which is the probe effects and not the system itself at this point. Okay, then there's lots that happens, and I'm just going to show you the state update rule for non-selective measurement here. Okay, so by non-selective here, I mean that you do a measurement of the probe, and there's no filtering conditional on which probe effect is being observed. So here I have my updated state after I do this non-selective measurement, and it's a state for A, and A is an element of our system observable. So this has to do with the system, right? That's what we want, is we want to know what the updated state of the system is. This is just the adjoint of the scattering, theta is just the adjoint of the scattering operator that I already showed you. And of course, we're going to need some initial state information. And so we're going to prepare our probe and system in omega cross sigma. So this is going to be the right state to assign over our uncoupled algebra in the region M minus, which is everything outside the causal future of our coupling region. And so this is introducing the assumption that you need that we're preparing our probe and system states in uncoupled, and that they're uncorrelated at the beginning. Right? And then you couple them in the K region, and then that's what the measurement is. Okay. So I want to say a couple things about interpretation in my last few minutes here. So this is the picture I had from the beginning. And so we do have a scattering theoretic picture of over finite regions. So K again is where we have our interaction between our probe and our system. So we have this kind of picture where, of course, so the nice feature of this is the scattering operator is that everything's nice and lattice covariant. So this means we're using the regions M minus and M plus. So like so these arrows are not time evolution, and that's maybe the main point here. But if you think about what happens like before you do your experiment, but now we're talking about all of M plus, right? So that's going to include the side cones as well. So those are not before necessarily. What I've put in blue here is you start out with a state that's appropriate to assign over the uncoupled algebra. Then there's this actual state that we have and this actual coupled algebra. There's something happening in the middle that's important physics. And then at the end, you have this other state, which is also a state over the uncoupled algebra. And so I think the right way to think about this in this picture with these algebraic states, which are sort of vicariously associated with space-time regions, because the algebras are really the things that we define over the space-time regions, then we define the states over the algebras, is that we have this one actual state of the system at all times, and then I like to think of the of omega and the updated omega state after the non-selective measurement as being counterfactual, and here in and out is really in scare quotes because it's over M plus and M minus, as I've been stressing, that are appropriate to assign to the system in these regions, insofar as they generate the correct probabilities for measurement outcomes. So,
right, I mean, this is puzzling me too. It seems like if there's a tendency in the philosophical literature to think, oh, we can slide from the kind of operationalist talk to, well, the observable are some kind of local properties, determinable properties of region. This throws a wrench into that. But the way to kind of, I think, to get out of it is to think, what they were trying to model originally were, again, like the things that you could do in the region. If you have a Cauchy surface, and you've got essentially some sort of formulation of determinism, things you can do include like time evolving and calculating. So it's like the algebra observables for a Cauchy surface includes sort of intuitively all the things that are like local determinable properties, plus all the things that you can calculate from all those local determinable properties, which is essentially everything on the dependency region.
So let me maybe put it a different way. I called it a problem, and maybe that's what's bothering you here. So I think that I think this might make you think, okay, so then what's special about things I do in lab regions, right? And how do I represent the thing that's probably most important here to this operational point of view in general is when I do a measurement in a lab, it's in my lab, right? And how do I represent that in this framework? So I think that's where the rest of this does a better job than you, yeah. But I agree, like you can just say, okay, well, I really mean the minimal region. You can make it bigger if you want, but you're right, it's like, that's what you can predict using the thing I do in my lab region. So then the comeback is, okay, well, but how do you represent what you do in the lab region?
So I'm gonna move Connor up in the queue. I have several other people.
I think I have reason to worry, and it's either regarding just a portion of this, or it makes me worried about my talk tomorrow, because it's
Okay, so worry about my talk today.
well, regarding the time slice axiom, to my understanding, it can be stated independent of the dynamics, insofar as all that you need to do basically is to, obtain a diffeomorphism between
Yeah,
closure surfaces.
You're right.
And like, what does that, or like, if that's the case, what does that do for this story?
Okay, good. So let me explain, you're right. And so let me explain more carefully.
Mhm.
So I said existence of dynamics.
Correct.
So it's worth emphasizing, which will probably come up later in the questions, that all of this is done at a very abstract level,
Mhm.
right? So I have not constructed anything
Correct.
more concrete
Mhm.
than a star. I haven't even constructed a model of this, but there are, like of the star algebra, right? So this time slice property is entirely at this level, at the level of an abstract requirement we're going to place on any dynamics we would add in
It's like
to make it concrete.
a condition for what
Right.
the dynamics can exist.
Right, exactly, yeah. So existence of dynamics, even in that abstract sense, you're exactly right.
Right.
That then, like when you actually go and do it and look at particular dynamical implementations of this thing,
Right. Okay. Yeah, that correct.
does that help?
Yes, no, that thanks.
Good work.
Yeah, thank you for the talk, Greg. It's useful. One of the things that I was discussed, right, about the Fuster formalism, right? The particular thing that, I like it very much. The particular thing that does bother me though, right, is this connection with practicality in the following sense, right? We're using a quantum field, and of course, we don't have a measurement theory for QFT. We don't know how to, in absence of all these proposals, right? We don't know how to state updates the QFT because of Sorkin-like problems. Now, they use another quantum field as a probe, right? And then the problem is who measures the measurer, right? That's the main issue. Like, if you have problems measuring a quantum field and you use another quantum field as a probe, the problem that I see is like, well, an important part of the measurement problem for me is the extraction of information by an experimenter, right? Or by whatever, the incorporation of the information acquired to the formalism. Now, if you need to deal with something like with another quantum field, you're gonna run into the same problems, right? And also you have the extra issue that most of the measurement apparatuses that we consider in labs are bound systems. By most, I mean like almost all of them, bound and localized systems. Now, localized, they could choose a localized mode for QFT, but how much do they connect with physical apparatus is something that I do doubt.
Yeah.
And the second is like, well, we don't know how to solve bound systems in QFT except for like the odd example, right? So those are the main, within the main two things that.
Yeah, so there's two things there. We're gonna put you on the panel for this, so I'm gonna ask you to elaborate on the second
Okay.
thing about this is an idealization, right? And actually, I should say, I've only introduced here the initial implementation of this idea, and there's asymptotic observable kinds of versions, and it attempts to make it more move more in Eduardo's direction. So the second point about this being an idealization and how you physically implement it, I'll let Eduardo talk about in the panel. The first point is also important, right? So in quantum measurement theory, the starting assumption is that what you're trying to do by connecting your probe to your quantum system is you realize that there's this whole chain of interactions that you're trying to model when you have a measurement, you could bracket the measurement problem, and that comes later on, but even at the point of doing quantum measurement theory, you're connecting the like quantum description of your probe to the sort of quantum mechanical description of the probe to the quantum mechanical description of the system, and then there's going to be like how does that actually issue in classical descriptions of like measurement outcomes, right? So the move in quantum measurement theory is to bracket that whole part that happens after you couple the quantum mechanical probe to the quantum mechanical system. In QFT, we're helping ourselves to this, in this version of the AQFT framework, we're helping ourselves to the analogous assumption that you have the QFT system, you have a probe which is described using QFT, and then you forget about the other links in the measurement chain, right? So that's what you're, and they're very explicit actually, Huster and Berg, that they're not aiming to analyze the whole process, just these two pieces of the links in the chain.
I
So
think
yes,
that-
this is an important thing to emphasize about the limitation of what's being done here. There's further debates between Eduardo and Chris Huster and everybody else about like how useful that is, right? So there's the practical question Eduardo will talk about later, but there's also the question of the assumption that you make in quantum measurement theory is that you can have adequate control of your device, right? So I think that's the main thing that's coming in here. If you have everything done in quantum field theory, like how does that, how do you control a quantum field theoretic system, right? Do you need to then couple it to a non-relativistic detector in order to get anything out of it? And actually, I think this is maybe, I think Dan takes a harder line on this than you do, right?
Yeah, no, I think, yeah, I agree. There's one thing about, so maybe a quote by Chris Huster, right, I like a lot for that. He says, like, well, the assumption is that somewhere, someone is able to measure something somehow.
So, and actually, I think, so this is important, and so this is why, so there's gonna be a review
It may be,
paper.
the quote might not be exact, but almost like that. Actually.
Yeah, no, so, and I think that is a fine quote to use, but I think putting it in the right context is important, which is
Right,
the
I
point I
agree.
just put it in. So that's what you say when you do quantum measurement theory.
Yeah.
So then, in non-relativistic quantum mechanics. So then the question is it different when you move to QFT? Are you less entitled to that assumption when you move to QFT?
Okay, Carlo.
Doreen, I found you super interesting, and very nice. It's bring to light specific issues in quantum field theory that seems extremely important. The comment I had, it's sort of vague, it's not sharp. What this sounds to me, listening, it's strongly a statement that one of the last transparencies that if you want to think in terms of state at some time, evolution, measurement, projection, this is the new state, that's what the world is, and then something happened, measurement. That doesn't translate easily in quantum field. That's very strong. Even a naive Heisenberg picture doesn't translate easily. Perhaps a less naive Heisenberg picture can be used as a name for what we're doing in some sense. Now, what all this seems to me, listening to you, at the end of the day, what we're talking about are probabilities. Probabilities are probability of something. So at some point, there's something that happens, whatever it is, with a certain probability. So there are somewhere there are facts, and we all agree at the end of the day. And whether we use whatever we use at the end of the day, there's no debate in lab what is actually. So those are solid. What seems to be saying here, that what screams to me, maybe not one of people which have different is that the very notion of a state as a representation of the actual things that happen there in reality, especially if I think that the state is localized in space-time, is just not the proper description of what goes on in nature, because the state is a much more subtle thing, which has to do with a way I use the actual facts to compute probability of actual facts, but in a way that cannot be, you cannot give so naturally an ontological weight of, okay, that's how things are, and the state evolving nowadays here in the city. So much so that in construction, essentially what you have is that regardless that to implement the condition, if I had seen this, that would be. So it seems to me all this is screening against any ontological way to the local state.
Yeah, so I would say without the ontology part, the first thing to do is to figure out, like when you move to Q, like, and I think this is one of the nice things about Alex's papers, it makes us think about this harder, right, is like, what exactly was the shift that happened between non-awareness and quantum mechanics to make the first formulations of QED possible? And it's just shifting away from the idea that you have an instantaneous state that evolves over time. And then, so then I think the point that keeps coming back is really what becomes important then is not the thing, so like go to a Hilbert space representation, it's not the state vector. What becomes important is the endpoint functions, right? Or the expectation values. And so that's really, I mean, I think this is something that Eduardo stresses in his work that is common to so the algebraic state, what is it? It's like a bunch of expectation values, right? In Eduardo's work, it's the endpoint functions as well. So instead of thinking of the vector in Hilbert space as being the thing that's the representative of the state, then it makes sense to shift to thinking about expectation values.
David and then Alex.
I want to draw a different conclusion about the measurement problem
Yeah.
from the one you put out. I mean, the conclusion I draw is this is why it's a mistake to formulate the measurement problem in terms of measurement theory in the first place. I mean, I think that you're absolutely right, of course. The traditional way of formulating the measurement problem says, here is unitary quantum mechanics, here is the collapse theory, and now here are the various dynamical inconsistencies that come from that. And I think there are independent reasons why that's a bad way to formulate the measurement problem. But when you try to apply that scheme to QFT, we end up saying, well, to even get a measurement problem in the first place, we need a measurement theory. And since we're so unclear about the measurement theory, we aren't even clear if there's a measurement problem or anything like that going on. And
So
that's
for the
clearly
record,
wrong.
that's much stronger than what I said. Yes.
No, I know,
yeah,
it's
yeah,
not,
no,
it's
I
not
know.
you said, but
Oh,
that's
I said that before you said, I don't think that's what's going on. I was hoping you did think that was what's going on.
no, I think that's what you think's
Yeah.
going on, but I think it should, in a sense, that's the logic of what's going on there. If one thinks that one gets the measurement problem because of the clash between Schrödinger dynamics and things and a set of collapse rules, and if we don't even know what the collapse rules are in QFT, then we sort of don't know if there's a measurement problem or what it looks like. And Madison's obviously wrong. I mean, QFT, and I don't take you to the argument, but I mean, QFT has superpositions, including on a macroscopic scale, it has interference, it has a probability rule, and yet it has phenomena that mean interpreting the probability rule as probabilities over underlying unknown goings on isn't possible. It's got Bell type phenomenology.
So let me reframe what you just said in a way that you maybe didn't like. Who knows? Okay. So one of the things you emphasized in the talk yesterday was the importance of the endpoint functions, right? And so so think about it. This shift that happens, as you point out, we don't even know initially what the measurement theory. Maybe we're now trying to figure this out. What the measurement theory is for quantum field theory. So then. And quite clearly, there's some sort of thing that's like a measurement problem there, even if it's not exactly the same thing as we find in non-relativistic quantum mechanics. Bracket that question for the moment. But like the reason why we didn't have a measurement theory is because we started to realize that we could just do this asymptotic scattering type measurement setup that works perfectly well for like lots of like scattering type problems that you would collisions that you would want us to solve for. So it does seem though that in order to get back to this important question of like what becomes a measurement problem in quantum field theory, you do want to have an idea of what local measurements would look like in quantum field theory, right, and how you represent it.
Maybe that's right, but no, that's not a good rephrasing of what I want to say. I think we get a measurement problem in QFT because we don't know how to interpret and make, modulo iterating solutions to the measurement problem.
Yeah.
We don't know how to interpret and make sense of unitary quantum field theory. We can see that as a problem even before we try writing down a measurement theory. If we want to write down a measurement theory where the state dynamic evolves over time, as a potential, and who want to take that not just as a useful tool in quantum information, but as a solution, as a way of solving fixing the measurement problem, then that starts looking like a solution to the measurement problem. That's the first step of that theory. But I think we can see there's a measurement problem right from the get-go before we ever start trying to build a
Sure,
measurement
we
theory.
can see that there is a problem of some type. What I'm pushing is, in order to see what the problem is, I think you do need to move in this direction.
Why though? I mean, I think we can see what the problem is. The problem is we can't prima facie interpret the state representation because of Schrodinger's cat, and we can't interpret it probabilistically because of interference.
Well, but didn't we just say that like if you're thinking about like the instantaneous state that you have in non-relativistic quantum mechanics and trying to understand that in quantum field theory, that's going to be problematic, right? If you're thinking about like measuring those kinds of things.
Well, it's going to be problematic when I want to update it by the sake of update rule. It's not going to be problematic if I just want to read probabilities of it, except that those probabilities aren't going to be straightforwardly interpretable because of interference.
Okay.
So I'd like to
Yeah.
hold this for the panel and give Alex a chance to speak.
Yeah.
A rather compact question. I was wondering whether, since you look also a bit like in the into the kind of traditions from which this draws,
Mhm.
regarding the formulation of the problem in terms of like finite time scattering,
Yeah.
something that I looked at in the aftermath of that paper and also with James a bit. Is there any sort of tradition that they draw on there, or is that just any?
Yeah. So so there's a series of papers by Helwig and Krauss in like 1969 and 1970, which are actually where Fuster and Dirk get the idea of doing this finite time scattering theory from. So like that's more like in the it's kind of a mix. It's not, and those papers have also been picked up. So they do a couple of things. One thing they do is the finite time scattering theory type idea and a different implementation. That they're also interested in like a Lorentz covariant version of Luder's rule. So one of the things that's in the background here is you might think, okay, Luder's rule, it's not Lorentz covariant. If we just make it Lorentz covariant and we solve all the problems, turns out that's not true. You need to do something a lot more elaborate like this in order to get out of like the Sorkin type problems.
Okay.
Okay, well, let's wrap it up there, and thanks, Doreen.